So this video is about how we calculate the pH of different acids and alkalis. I'm going to do a different video on indicators and pH curves. Before we continue, you can actually do questions 1A to C in AC18, as that is a bit of revision on titrations. So today we're going to look at how we actually calculate pH using an equation here. And we can also calculate the concentration of H plus ions in a solution using pH by rearranging this equation. We're going to look at something called the ionic product of water, because we need to know this value to work out the pH of strong bases. And then we're going to look at how we work out the pH of weak monobasic acids, and we need to use Ekman constant or dissociation constant for a weak acid to do that. So the pH scale was devised by a Danish scientist who was doing some research on proteins and the effects of H plus ion concentration on proteins. And his scale basically shrank the large range of concentrations you can have for H plus concentration into a smaller scale. So we used log to the base 10 before to shrink the scale of difference in successive ionization energies for a particular atom. So pH is simply calculated as the log to the base 10 of the concentration of H plus ions. Since the concentration of H plus ion solutions are often below 1 mole per decimeter cubed, we often find that the log of the concentration of H plus ions has a negative number. So for example, if I have log to the base 10 of 0.1, that would give us minus 1. If we have log to the base 10 of 0.01, then we have minus 2. So often, if we just use log to the base 10 to calculate pH, we're going to get a negative number. So what we do to cancel that out, we put a minus in front of the expression to give a positive number for pH. So pH is minus log to the base 10 of the H plus concentration. In the exam, you need to be able to work out the pH for strong monobasic acids like nitric acid or hydrochloric acid. And you need to be able to work out the pH for weak acids or weak monobasic acids like phenol or ethanoic acid. And we need to be able to work out the pH for strong alkalis like sodium hydroxide or potassium hydroxide, etc. And I'm going to do it in this order. So we're going to look at strong monobasic acids first, then strong alkalis, and then finally weak acids. It's really easy to work out the pH for strong acids, as we can work out the concentration of H plus ions if we know the concentration of the acid, because the concentration of the acid will give us the concentration of the H plus ions when it's fully ionized. So when the acid dissolves in water, as a strong acid, it will fully ionize. So the concentration of H plus ions will be equal to the concentration of the acid we start off with. So if we have 1.5 mole per decimeter cube of HCl in solution, all the HCl molecules would ionize or dissociate into H plus ions and chloride ions. So we know the concentration of H plus ions as it is the same as the HCl, because the stoichiometry of HCl to H plus is 1 to 1. So the concentration of H plus ions would be 1.5 mole per decimeter cube for this solution. And plugging 1.5 into log to the base 10, we get minus 282. And if we put the minus in front of the minus 2.82, we get a pH of 2.82. We can rearrange this equation to give us the concentration of H plus ions if we know the pH. So what we do, we remove the minus sign from this side by putting minus on both sides. So I do minus pH equals minus log to the base 10 of H plus. Well, that gives us a positive on this side because a minus is a positive. So we'll have minus pH equals log to the base 10 of H plus concentration. So what we do next is we use the inverse function of log to the base 10, which is 10 to the power of, and apply it to both sides. So we have 10 to the power of minus pH equal 10 to the power of log to the base 10 of H plus ions. 10 to the power of log to the base 10 would cancel each other, so we'll be left with just H plus concentration. So we have So here's our equation to work out H plus concentration if we know the pH, which is 10 to the power of minus pH. So here's an example of a question where we got the value of pH of a strong monobasic acid, which fully ionizes. So we can work out the concentration of the acid if we know the pH of the acid by using the pH and converting it to the concentration of H plus ions. And since in the strong acid, the concentration of H plus ions will be the same as the original acid, then we can work out the concentration of the acid. So in this case, we have pH of 3.51 for the acid, and we take 10 to the power of minus of that pH, so that's going to be 10 to the power of minus 3.51, and that gives us a value of 3.09 times 10 to the minus 4 moles per decimeter cube, 2 free silicon figures. So the concentration of H plus ions is this, which will be the same as the concentration of the original acid, which is the what's requested for the question. You should now be able to do questions 2 to 4. What we're going to do next, we're going to look at how we can work out the pH of strong alkalis using something called Kw, or the ionic product of water. So I'm going to explain what we mean by ionic product of water, or Kw. So we start off with pure water, and even though it's pure, it does ionize very slightly to form H plus ions and hydroxide ions. So even with pure water, this does happen. However, the equilibrium is very far to the left-hand side, so there are very, very little amounts of H plus and OH minus ions. So only 1 out of 5 times 10 to the power 8 molecules will ionize, and that's a very, very small number. Nevertheless, we can actually still write an equilibrium constant for this equilibrium. So this is the equilibrium expression for this equilibrium, and we've seen Kc before when we did equilibria. So for this ionization of water, we have this expression. We can rearrange the equilibrium constant expression for the ionization of water by moving this denominator here to the other side. So what we have is the equilibrium constant times in the concentration of water equaling the concentration of H plus ions and the concentration of hydroxide ions. Since Kc is a constant temperature, and at a given temperature the concentration of water for any sample will be the same, these two are constants, and we can combine these together, and we're going to call this Kw. So Kw is just these two values multiplied together. So since these two are equal, Kw is equal to this, and this is called the ionic product of water. In maths, product means multiplying two numbers. So these are ions, so this is the ionic product. You should be aware of the value of Kw, the ionic product of water, at standard temperature and pressure. You can actually calculate it since we know that the pH of pure water is 7 at 25 degrees C. So we can substitute the value of 7 into H plus concentration, because we know that H plus concentration is 10 to the power of minus pH. So in this case, it will be 10 to the power minus 7. Since there will be 1 proton and 1 hydroxide ion for every 1 molecule of water ionizing, the concentration of OH minus will be the same as the concentration of H plus. We can then substitute these values, which is that, into the equation, and we can work out the ionic product of water. And it works out to be 1 times 10 to the minus 14, or simply 10 to the minus 14. And notice the units is the squared of the units of concentration. So at 25 degrees C, the ionic product of water, Kw, has a value of 1 times 10 to the minus 14 moles squared decimeters cubed minus 6. You should now be able to do questions 5 to 7 in AC18. Now that we know what ionic product water is, or Kw, we can use it to calculate the pH for strong bases. So here we have a strong alkali or strong base, and we have 0.1 mole per decimeter cube of this sodium hydroxide, which fully ionizes because it's a strong base. So we can use the ionic product of water to calculate the pH of this solution. All we do is rearrange this equation here for H plus concentration, and since we know Kw at 25 degrees C and we know the concentration of the hydroxide because the sodium hydroxide fully ionizes, we can work out H plus concentration. And then what we do, we just use minus log to the base 10 of the H plus concentration to work out the pH of this alkali. So rearranging this, we get this. Since we know the value of Kw at 25 degrees C, as it is always 10 to the minus 14 moles squared decimeters cubed minus 6, and we know the concentration of the hydroxide ions to be the same as the concentration of the alkali, because a strong alkali fully ionizes, so the hydroxide ion concentration should be the same as the concentration of the alkali. If we put the numbers in and put the units in, we get this value, which is 10 to the minus 13 moles per decimeter cube for H plus concentration. So all we're going to do is going to substitute this into here, and we get a value of 13. So minus log of 10 to the minus 13 is 13. So here's another example. In this case, we've got a dibasic base or alkali. So for each unit of barium hydroxide, there'll be 2 units of hydroxide ions formed in its ionization. It is still a strong alkali, so it fully ionizes. So if we have 0.1 mole per decimeter cube of barium hydroxide, there'd be twice as many moles of the hydroxide ions. So therefore the concentration will be twice as big as well. So we can work out the concentration of H plus ions by rearranging the ionic product of water equation, and we have H plus concentration equals the ionic product of water, which is 10 to the minus 14, divided by the concentration of the hydroxide ions, which we've got here. So we put the numbers in, we get 5 times 10 to the minus 14, minus log to the base 10 of 5 times 10 to the minus 14 gives us 13.3. Notice there are no units for pH, so we don't write pH as units. pH is just a number. You should now be able to do questions 8 to 9 in the booklet. So we covered what pH is. We've also covered how to work out pH for strong monobasic acids. We looked at what the ionic product of water is, and we can calculate the pH of strong bases using the ionic product of water. What we need to do next is we need to look at how to calculate the pH of weak bases, and to do that we need to look at something called Ka first, which is the acid dissociation constant for weak acids. So for weak acids like ethanoic acid, they don't fully ionize, but they partially ionize. So we show this by using a reversible sign. We can write a generic equation to show any weak acid by writing HA, where H is the proton being lost and A is the anion part of the molecule. So when it ionizes, we get the H plus ions and the anions. We can write a Kc expression for this. So here's the Kc expression for this equilibrium. Since this is a weak acid, we're just going to change the name of Kc to Ka, where A is the acid dissociation constant. For every acid molecule that ionizes, we get 1 proton and 1 anion. The concentration of H plus and A minus should be the same, since these are the same for a weak acid ionizing. So we'll have this, since these two values are the same. We can rearrange this to give this, and we can take the square roots on both sides to get this. So to recap, if we have a weak acid which partially ionizes, we can have a Ka expression, or the acid dissociation constant expression, as this, and since these two concentrations are the same, we can simplify it to this. Rearranging this, we'll get this expression. Since Ka values are very, very small, like H plus concentration values we saw at the beginning, we can use minus log to the base 10 of Ka to give us a value called pKa, in a similar way to converting concentration of H plus ions to pH. So pKa values are much easier to publish in tables compared to Ka values, as Ka values are often very, very small. Here I'm going to show you how to do question 12 in AC18 as an example how to calculate the pH of a weak acid using Ka. So we're given the value of Ka in this question, which is 1.7 times 10 to the minus 5. And we know the concentration of the acid. We know the Ka expression for a weak acid is the anion and the H plus ion over the concentration of the acid. And for weak acid, these two values are the same. So we can simplify it to this. So rearranging this, we will get H plus equal to square root of Ka times the concentration of the weak acid, in this case ethanoic. So we know the Ka value because we're given it, and we know the concentration of the acid as we're given it as well. We multiply these together, take the square root, and we get this value for the concentration of H plus ions. Once we know the concentration of H plus ions, we use minus log to the base 10 of H plus concentration to get the pH. So in this case, minus log of the concentration of H plus, which is this, we get 2.53. You should now be able to do questions 10 to 14 in AC18. So in this video we covered what pH is, which is minus log to the base 10 of H plus concentration, and we can work out the pH of strong acids because strong acids fully ionized, so we know the concentration of H plus directly. We can also now work out the pH of strong bases at 25 degrees C, since we know the ionic product of water is 10 to the power minus 14. Finally, we can work out the pH of weak acids using the acid dissociation constant and rearranging that for H plus concentration.